Howdy everyone and welcome back. Today we're going to talk about something a little simpler, I would say, something a little more easy to grasp compared to abstract things like electric fields and electric potentials. We sort of needed that to build up to this concept, but we're going to start talking about real life electrical components and starting off with one of the simpler ones, capacitors. So at the basic level, what is a capacitor? Well, capacitors are things that temporarily store charges, not like a battery chemically, but just hold charges in place. And so we have a basic capacitor here, probably one of the most basic ones we have. Is we have two parallel plates next to each other, and we have one with positive charges on it, we have one with negative charges on it, and in between there, we know there has to be an electric field that's created. So these charges don't want to be there. They would prefer to go flying off. The positive ones don't want to be there. They want to move away, and the negative ones don't want to be sitting next to negative ones. So what's holding them there is an overall voltage. So there's some potential difference here that is holding them in place. So a capacitor can have charge, it can have a voltage, and the connection between the amount of charge it has is its change in voltage between these 2 points and something called the capacitance, and that's essentially its ability to hold charge. And we can get this through geometrical arguments. It's things that have a greater cross-sectional area. So this A is this cross-sectional area here. Something with a greater cross-section area can hold more charges, and the capacitance goes up. Or something that has a smaller distance, so this distance d is this. If you put two plates and put them together, put these charges close together, this electric field is going to increase. You can hold more charges there too. So either way, you can create something with a bigger capacity to hold charges. That's all that capacitance means. So something with a higher inherent ability to hold charge times electric potential that's forcing those charges to stay there determines total amount of charge sitting on those plates. So something we're going to have to do a lot with capacitors is combine them. So the idea is if I have a bunch of capacitors that are nothing else really electrically going around in these circuits, I can actually take all these capacitors and replace them with one equivalent capacitor, and nothing else would have changed elsewhere in the circuit. We're going to have to do that for situations where capacitors are in parallel or when they're in series. So in parallel, we mean that if we're moving along this line, we can go several different directions and end up over here. That's what we mean by parallel. While in series, we only have one direction, and we have to pass through all of them. So to take all these capacitors and combine them in a parallel way, it's just like we're going and making one big capacitor and just increasing the area of it, adding all the areas of these together. That's sort of how we can think about this. So the capacitance, combining them, is really simple. We just add up all the capacitance from the individual ones and we'll get this total equivalent capacitor. So again, we're maybe not really replacing all these capacitors in a complicated circuit with one, but problem-wise, it's easier to do problems with one capacitor typically, and we'll see that in just a little bit. So to do for series, instead of adding them straight, we have to do sort of a weird inverse rule. So we add the inverse of all the capacitance together, and then we invert that in the end. So I have this -1 power over here, so we have to do essentially 1 over all this stuff in the end. This is stuff we can put in our calculator, stuff we can put in Wolfram Alpha, just trying to be clear about it. Okay, so let's start doing problems with capacitors, and we'll find this is pretty different from things we've been doing. It's not so abstract like fields, but sitting down with real mock-up versions of circuits. So here we have this is a battery, so we indicate batteries with one long side, one short side, and this is the side with the positive end, one with a negative end. So what that means is that if we had positive charges, they would move in this direction. So this is creating a voltage, and as we go around the circuit, this creates 9 volts. We'll learn in a bit that we'll have things like Kirchhoff's laws, that if we go in a path, eventually we'll have to drop 9 volts. So if I have a power point creating power somewhere, I have to have somewhere else where it's actually exchanging that power and doing something else with it. That energy doesn't just disappear. So we want to figure out a few things. We have two capacitors and they're in parallel. We want to find an equivalent capacitance for these two. So we'll have to find some way to combine them into one equivalent capacitor that we could replace both of them with. We want to find the voltage over each. We want to find the charge over each. We'll be able to do this in all a few steps. So the first step is pretty simple. These two things are in parallel, and the capacitor add rules tell us that we can just add them both together. So one is 5 microfarads, one is 12 microfarads, 5 plus 12, 17. Okay, so we can replace this with one equivalent capacitor of 17 microfarads and nothing would change in the circuit. So what is the voltage over each? Well, according to Kirchhoff's loop laws, which we'll technically learn later, but we can sort of invoke them now, we can go in any path here, so we'll have to get back to 0 volts. We add 9 volts, we would have to have dropped 9 volts here. And the same thing goes regards to this path. And we'll find that in general, if you have things that are in this sort of a loop like this, you have 2 items, they have to have the same voltage. Because if you go in a loop, have to add to 0 for this voltage. So if I gain 9 volts here, I have to lose it here, all with directionality. So that means voltage over each of them, just 9 volts. Pretty simple. So lastly, we want to get the charge over each of these capacitors. And fortunately, we can just go back to the equation we learned in the beginning. The charge over a capacitor is the voltage over it and its inherent capacitance. So we know all those things. We just found the voltage over everything. They were given the capacitance over everything. We can just plug in that into both of these and get our answers. We'll find that this one has a larger charge compared to this because it has a higher inherent capacitance. Okay, hopefully that makes sense. So let's do an example that's maybe a little more complicated. We have now a circuit with 4 capacitors, one here, one here, one here, one here. We have 1 battery. So we want to do something similar. What is the equivalent capacitance? What's the charge on each? Which is the voltage on each? Okay, so we have something that's a bit more complicated, and that means we need to break it down to an equivalent capacitor one step at a time. We can't just do it all in one step like last time. So when we have to look at it, we have to see in the most basic shapes what's in parallel, what's in series, and then we'll have to break things down one step by step into equivalent capacitors. So here we see these 2 things are simply in parallel. We have to be able to match it with the pictures that we have originally. If it doesn't look like that, we can't use any of the capacitor breaking down rules. Here we have 2 things that are in parallel, and you can see that we want to say these things are in series, but we can see it gets a little messy here. Branches. No, let's go at the simple pictures. These are obviously in parallel. We can compare that to the pictures in the beginning. Those have to be in parallel. So we can break these 2 into equivalent capacitor by simply adding them because they're in parallel. Now we get this circuit. So we can see these 3 things are clearly in series. And so we can do our additive rule with regards to things in series. So we do the 1/8 rule, and we go ahead, we do that. 3 of them, that's 1/8 microfarads. We find that the total equivalent capacitance for 1 capacitor replacing all these things is 8/3 microfarads. Okay, from here to get to the rest of the quantities, we can sort of move backwards. So we usually break it down to get it to the simplest form, and then from there we can start expanding out and usually working back with charge and voltage. We want to find the charge on each, so we need to use a few rules. So the capacitors in series have the same charge, and we're going to have to use capacitors in parallel have the same voltage. So this one comes from the one Kirchhoff loop law. I go in a loop, all the voltages have to add to 0. So that's going to tell us things in parallel have the same voltage. So capacitors in series, why do they have the same charge? Well, you can think about if I moved a charge Q away here, where does it go? Well, it has to end up on the next capacitor. The charge here ends up here. So these things, all these things in parallel have to actually have the same amount of charge. The charge doesn't get created or gets destroyed. It just moves from one thing to another. So we can find the total charge on this 8/3 microfarad charge. We know the voltage over it because this is a 9-volt battery, 9 volts. Put this equivalent charge in here, we get this charge. So we go back to this step and can ask, what's the charges on each of these things? Well, it actually is the same exact charge on this. They all have the same charge. It doesn't get split 3 ways. That actually would happen if it was parallel. It would have to share the charge. These don't have to actually share the charge. Each of them push the same charge to the other ones. Turns out then we just now have the charges for each of these. And the last bit, we want to get the charges now on 2 and 3. So these 2 have to share it. So if this one gives this Q total, it does get split 2 ways, and how much actually is going to depend on the voltages over each of them. So we can write this. We know that each of them are going to share that total charge between them, and we need another equation so that we can break this degeneracy here, because we can't tell if Q2 has more, 3 has more. Well, the thing that's true about each of these is that they have the same voltage. So I wrote an equation here. I don't think that's super obvious, but I really should be starting with voltage of 2 equals the voltage of 3, and you'll be able to use the equation originally, Q equals VC. Move the C over to the other side, you'll get this relation here, and then we can solve a relationship between these charges. So we have 2 equations with 2 and 3. We have this one, we have this one. we know from linear algebra, I have two equations, I have two unknowns. Now I can actually solve for them. And we can use substitution so for Q3, we can go and solve for it, put it in here, and we'll find something that's only in Q2. We can go and pull the Q2s out, then solve for Q2. It's Q total over this, sum here. Find this charge. And we can always go back and find the charge of Q3 by going back to either one of these equations. And now that one of them is known, we could just solve simply for the other. I just go back to this one, pull it in, solve for Q3, move Q to the other side. Now we have the charge on each of them. Last thing, we want to get the voltage over each of them. Now once we know either both the capacitance or the voltage or charge any two combinations of those three, we can just get the third one with Q equals VC. And that's what we do. We know Q and C of all of these, we can go back and solve for the voltage. And so if we put in those numbers, we find that they're just all happen to be 3 volts. That may not always be true. Any path that we go, we'll define that the voltage all sums to 0. So if this adds 9 volts, these 3 have to drop to 9 volts, and these 3 have to drop to 9 volts with this path. So maybe we won't always get to the same, but just happened in this case. Okay, thank you very much for watching. Hopefully this was informative. We'll keep talking about circuits. We'll keep talking about some practical stuff with regards to electronics in the future. Yeah, but thanks for watching. Bye.